Hello, Gophers. Hello, Gophers. There's lots of ways to say hello, Gophers. Here's another way to say hello, Gophers. And I can prove it. This is an amazing historic occasion. I'm not used to success, so this is kind of a strange feeling for me. It's incredible to me that Go has achieved a level of success that makes people want to get together and have a conference about it. I think that's wonderful, and I want to thank the organizers for putting this together, all of you for coming, and especially the entire community for making Go the success that it is. A lot of factors, I think, contributed to that success. You could argue that it's the features of the language, it's the lack of features in the language, it's the combination. I also think it has a lot to do with the design, the way we went about designing it and how it turned out. Of course, a huge part of it is the people who worked on it and what they did. And the passage of time refining and making things happen. And so today I'd like to take a look at that whole timeline and see what happened, how Go came to be, and where we are today as a result of that process. And to do that, I'm going to take a look, a fairly detailed look, at two programs. They're both historic. One of them is probably the first Go program most of you ever saw. And the other is essentially the first Go program of any interest that we ever saw. So both of those are historic. And the first one is the old Hello World. Here's the original Hello World. It was written in B by Brian Kernighan in 1972. So this is the first Hello World anybody ever saw. This is what B looked like. It was kind of an interesting language compared to today. It was a typeless, word-based, interpreted language. Of course, it was the predecessor to C. You can see intimations of C in the syntax. But you can also see strange things like put char of A, where A is this weird 4-character integer by name, and then put char of bang star N as a quoted string. So the question is, why is there a quoted string for a new line, but A is 4 characters? You might wonder about that. I wonder too. I have no idea. But anyway, that's what it looks like. Some people think that Hello World came from BCPL, but I asked Brian about this, and he said, no, he asked Martin Richards about it, and Martin Richards said it wasn't him, it was Brian. So as far as we know, this is the first ever Hello World, 1972. Here's the 1974 Hello World. This is the first Hello World I ever saw. This was in the Programming in C tutorial, again by Brian, written in 1974, and came as part of the Unix v5 distribution. And you can recognize that this is a C program now. It starts to look a lot like what I think even those of you who don't know C would recognize as a C program. There's printf, there's quoted strings, there's braces, there's main. Huge leap forward in 1978, C had a book. And there was a big change between the Hello World there and the Hello World there, which is it got a new line character. But this is the full source. You're still, for those of you in the know, this is still missing some pieces. And in fact, it wasn't until the ANSI standardization effort, which happened around '88, that it started to look more like the C of today, and include with an angled bracketed stdio.h on it is a mark that the library is now something you already talk about instead of sort of being implied. And this was actually written to the draft ANSI C. It hadn't quite been finalized yet when Brian and Dennis rewrote the book for the ANSI C. And there's actually a book copy came out in early '88. It was reworked slightly for later in that year when the ANSI C standard was finalized. And there was actually a change to the program, which is the appearance of void in the arguments to main. I was standing next to Ken when he learned about this, and he said out loud, "You got to put a void there." But you did. And it was probably the one thing where at the time I thought C++ was better than C. But that was I said C99. It's really C89. I'm sorry. That's just a typo on the slide. This is C89. Okay. That's a lot of little hellos. Let's get to Go, which is the one that we're here to talk about. Skipping ahead a few generations of languages, every language now starts with a hello world. It's basically where the world begins. I guess maybe certain communities look at it differently, but certainly in this sort of branch of language world, hello world is the starting point of your learning a language. The discussions for Go started in late 2007, and in early March 2008, we started writing the draft spec. And there was actually a compiler already underway by then just to have a playpen, and Ken was working on that. It was actually generating C output, which was problematic because of various interactions. But it was good enough that the very, very first Go program was actually written with that, although it was so buggy and hard to make work that it almost doesn't count. But once the specs started to come together, we could actually write a proper compiler, generate native code, and it was time to write tests. And the very first checked-in test included this example. So this is the first hello.go, and it's dated June 6, 2008, and it looks different from the hello.go of today, and that's what I'm going to talk about. So you can see it looks a lot like it, but notice that, for instance, print has no parentheses on it. It was actually a keyword, and main was an integer-valued function, and you had to explicitly return a 0. But we had no printing mechanism other than this built-in print. It's a bootstrapping thing, and that's why it's still there. I think if it hadn't been for bootstrapping, it wouldn't be there at all. But by June, we decided that since main was always going to return, if you could call that the clean return, so we got rid of the argument to main, made it just be a niladic function that returned nothing, and when it returns, you get an exit call. So that's June, but it's still got no parens on the print. The parens came in a couple months later in August, where we were starting to clean up the language a lot. We wanted to get rid of these magic words, and print became just a pre-declared identifier as a built-in function, not really any special status beyond that. And this version, I think, actually runs. So there's a working print. That's the first workable, by today's standards, hello.go. But we're not done yet. On October 24th, 2008, I checked in a CL that read printf as we know and love it. And so from now on, we're talking about the printf version rather than the built-in print version of Hello World, which is not actually the way the test version runs, but it's the one we're going to talk about. And this is very close to today, except for two details. One is there's a lowercase p on the print, and there's a semicolon, but they went away. On January 15th, 2009, after a long discussion, I'll talk about more in a minute, casing went in to specify visibility, and so capital P came to printf. And for the first day or two, that looked so strange and weird, and we were kind of uncomfortable. But about 2 days later or so, we realized this is one of the best decisions we've ever made, this case for visibility. So that was a big step. And this one runs still. But on December 11th, 2009, after the open source release, which was in November, we finally got rid of the semicolons. So this is the printf Hello World version that we all know and love. So it took us a while to get here. I mean, I've gone through it in about 5 minutes, but there's really 32 years worth of Hello World refinement. And I want to talk a little bit more about that, because there's a lot of history in that sequence. But I want to make sure you understand that although we talked about C and the Hello World timeline starts with B and C, Go is not just some variant of C. It's actually profoundly different from C. We started from C, or the first mail ever between us about Go was from Robert and started with, we start from C. But it's got ideas from so many other languages, so many other threads of thought, some original things, that I wanted to make sure that I made it clear that there's a lot of influences on the language, both direct and indirect. It looks most like C because that's where the statement and expression syntax comes from, but most of the semantics comes from other places. The declaration syntax is out of Pascal. The Virt languages module, the various modules in Oberon's delivered something close to the package form, although again, it's a little different. Of course, the whole CSP branch of concurrent programming has a huge effect on Go. The semicolon rule was lifted right out of BCPL, which most of you have never even seen, let alone written in. The way the methods work is much closer to Smalltalk than, say, Java or C++. My great contribution is the two magic tokens, left arrow and colon equals. They came out of Newsqueak. The IOTA keyword came out of APL, kind of, sort of. And there's lots of other languages that were in the room we're talking about that influenced it, either because of ways to do things or ways not to do things or how to think about things. And so I really don't want you to think this is some C thing. It gets called that a lot, and I think it's a mistake. It's actually a language influenced by a tremendous, rich history of languages, but unique unto itself. Which brings us up to today. Here's the hello.go that you No, I changed a couple of things here. First of all, I went back to println from printf. I'll talk about why I did that in a minute. And also put in UTF-8 in an interesting way by acknowledging the Japanese Gophers, of which I think there are quite a few. Are there any Japanese Gophers here today? Yes, good. Okay. So I'm going to break this program down because it's trivial. You all know it. You all have seen it. And yet, there's actually a lot of thought behind every single piece of this program. It has 16 tokens. You could probably figure out what those tokens are. I'm going to talk about every token. Don't worry, there's more here than you think. First of all, package. Actually, I think packages might have been the thing that we spent the most time talking about in the design of Go because we knew how important it was. We knew that wrapping up things into a library used in a way that was controlled and stable gave you a chance to do things like solve build problems, deal with dependency issues. You had to control dependencies in order to get the build times to be fast, which was critical to us. You had to make the packages be clean because that makes programming a large possible with lots of groups sharing code and working together, but without breaking through the walls between the components. You wanted the package system to somehow express all the information needed in order to build. You didn't want to have makefiles or other fancy build systems necessary. You wanted the Go source to express what was really going on. We wanted to make sure that circular dependencies didn't happen because that controls the size of the binaries, the speed of compilation, how much linking has to happen. There are no sub-packages. I don't know. There was a little talk about that. I don't really remember what the thinking was. But even though there are subdirectories in the hierarchy, they aren't sub-packages. There's no such concept. Every package is a unique standalone thing. We separated the idea of package name and package path. Pretty simple. Turns out to be profound in what effect that has. The whole idea of visibility being package level rather than type level, the way it is, say, in Java with public and private, is a pretty big deal. And I'll talk a little bit more about that in a minute. Most important, I think, something that I don't think most people really think about, you just use it. Within a package, you have the whole language at your disposal. This is because the visibility rules work the way they do, but also because we made it this way. When you're writing a package, you're basically writing a standalone Go program on all of its pieces. And you define the boundary of the package, which is what your clients are going to use. But inside, all the information is available to everybody. There's no so-called information hiding. As Bruce Ellis once wrote, who am I supposed to be hiding it from exactly? I wrote both pieces. And so I think that's actually an interesting design point. And of course, it came out of the modular branch of languages, but it's very different from many of the other common languages in use today. And so I think it's worth recognizing that package is actually kind of special to the way Go works. Okay, the next token is main. Now, this is not the function main. This is the package named main. It's one place in the whole thing where the C legacy really shines through. That word just flowed from B to C to Go directly. It was originally called capital main. I have no idea why. I think it's my fault, but I don't remember why I thought you wanted that to be capitalized. Anyway, it went away. So there was originally a capital main package and a lower main function. And initially, that's how program execution began. But what really matters is it's special because of the main package is the root of the initialization tree. It has nothing to do with where the program starts execution proper. It's actually how initialization works. I'll talk about that in a minute. Import. Import is the next token. Import is the mechanism you use to load a package, how you get a library into your world. Unlike a lot of other ways it could be done, in Go we decided right up front, almost implicitly I think, that import would be defined by the compiler. The compiler would actually do the work of doing the import, as opposed to, say, a text processor or some other mechanism. We worked really hard to make sure that the design made it very efficient. For instance, the export data in a package is right at the beginning of the object code for the package. So the compiler only has to read the very beginning of the file. It doesn't have to read the whole library in order to do the compilation. We worked hard to make it linear. I've talked about this a lot before. This is the notion that you pull the dependency information up into the packages from your dependencies so that someone compiling against your package doesn't have to talk to the packages you depend on. It can get it all from doing the single import. That means that the number of files you open when you compile a program is just the number of packages you import plus the source file itself. It's also interesting that you don't import a set of identifiers. You actually import an entire package. The concept of package being the thing you get is not exactly unusual, but it's different from the way a lot of other the way a lot of other things work. I'd also like to point out that there used to be an export keyword That was how we originally controlled visibility. It was pretty unwieldy, and of course you know what we did to fix that in the end. But it was there for probably about a year. There's actually a CL that deletes it. That was kind of fun to watch go by. Okay, then we come to FUMPT, the string that is the package path. This is a very short package path, of course. It's in the core libraries. But it is just a string. It has no special meaning to the compiler. It was deliberately decided very early on that the import path, separate from the package name, would be just a string, and the language would not define the meaning of that string, so that we could change the meaning or put interesting information in it later if we chose to do so. And of course, URLs were what we had in mind, but who knows, maybe some other mechanism will come up. There's already talk about doing versioning through the package path string, that kind of thing. That was always planned to be an open thing. It was not. It was just an explicit decision. This allows for future growth, which of course is exactly what's happening. Then the func keyword. Now, this was a big step from C. It's actually borrowed much more from the Pascal side of things, because that's where most of the declaration syntax comes from in rough strokes. Having an actual keyword introduce a function is very different from the C family. Of course, very common in a lot of other languages. It makes it a lot easier to parse the language, because a keyword really starts things going when you're going to do a declaration. You don't have to deal with figuring out whether it's a type or an identifier, what's going on. And it's really important that Go be easy to parse. It makes tooling easier. It makes it easier to understand the programs when you just see them on the page. It also makes it a lot easier to have things like function literals or closures, because the grammar inside a function body is a lot easier to understand. By the way, the original keyword was not func, it was function, because that's what it is. It's a function. And it went away on a well-known date. This is a mail thread on February 6, 2008. Ken mailed Robert Griesemer and myself. Larry and Sergey came by tonight. We talked about Go for more than an hour. They both said they liked it very much. P.S. One of Larry's comments was, "Why isn't function spelled funk?" So I responded, I mean, why not? This sounds good. We already had type and const. Why not just shorten function down to funk and fit right in? Robert objected a little bit because he thought it wasn't important, but he rapidly came around. And so I think the next day, function got shorter. So you can thank Larry for those keystrokes going away from the program. Okay, the next main token, this is the function name. And it is where the program starts executing, of course, except it really isn't. What's important here is initialization. That happens before main starts. And in fact, the whole story about how initialization works in Go had been rattling around, particularly in Ken's mind, for a long time. Before Ken left Bell Labs, which was about the year 2000, maybe a little before, the last thing he did to the Plan 9C compiler was try to inject some notion of controlled initialization into the compiler and language. And I don't know if that code still exists in the compiler, but it was there for a long time. It didn't quite work. It's actually difficult to retrofit into C. But he kept thinking about it, and when Go started, it was one of the things we wanted to get right, because initializing your program is very important to getting it to run well. And it's a trivial point, but a lot of languages don't spend any time thinking about it, and you can get in very difficult states with unclear initialization order, random initialization order, and strange behaviors. And the key point about the main package is that it is the root of the initialization tree, and although it took a long time to figure out how to do it, the mechanism for getting the dependency tree to be executed correctly by initialization turned out to be very easy to do, although we had a lot of thoughts about much more sophisticated, fancy ways to do it that we later abandoned, including doing initialization in the linker. What happens now instead is the compiler generates little bursts of code that execute the inits sort of recursively almost, resolving them in the correct order. It's pretty trivial, but it took a long time to get there. And as I said, been thought about for a long time. It also has a pretty big effect on how packages work, because inits are one of the ways you can get around the strict requirement that there's no circular dependencies. It gives you a foothold for that. So initialization isn't talked about much in Go, and it's actually a really important feature for how programs are built. It's often neglected. And of course, I folded two tokens together here. Look, Ma, no void. We got rid of void. When you have really good function syntax, you don't need that kind of crutch. It was there because in C, because of course the difficulties introduced by a change to declaration syntax, but it's not necessary anymore. There's nothing after this parent. There's no return value from main. It just exits when the program exits. And there's also, therefore, no arguments to main. in a related point because the runtime handles it. It's kind of an operating system dependent feature. And so we put them in the operating system dependent component and put no return value in to make the function nicer to look at. It also makes the hello world program shorter, always a benefit. And although this program doesn't have any return values or interesting function argument syntax, let me spend a moment just talking about that because we spent a long time and many versions and iterations sorting out what function syntax would look like, how you specified the arguments, how you specified the return type. There were arrow operators and strange groupings as we tried various experiments. And finally, I don't remember the exact order, but around the time that we finally decided what method syntax would look like, which was to put the receiver inside parentheses, the functions then just became three parenthetical things, the receivers, the arguments, and the return value. But it took several months to sort through that because we're stupid. Brace. Well, the opening brace, of course, puts it firmly in the C family of languages. We never considered using white space for indentation. I just think it's a profound mistake in programming language design to have your semantics depend on invisible characters. I don't. There's a reason for that. I've been burned badly by bugs introduced by invisible characters causing changes in things, particularly when you combine, for instance, Python through Swig embedded into C and C++ and various other combinations like that. And it never occurred to us. We were going to make it a nice, controlled, syntactically structured language. It's also not square brackets. We had a meeting with Sergey after the meeting with Larry and Sergey several months later. I think Russ was at that meeting too. And Sergey asked why he had to type a shift when he wanted to start a new block. Why not make it square brackets? And, well, he didn't win every argument. But a good point about this is that there's no new line after there's a new line after the brace. It's not before the brace. You can't put it before the brace. This is an unintended consequence of the semicolon injection rules, which went in December of 2009. As I said, it was that notion, the way that works, which is that the grammar has semicolons, the lexical analyzer injects them for you under certain conditions. That came directly out of BCPL, although of course the rules are a little different. But it meant that you couldn't put the brace on the next line. That was kind of an, oh, sorry. But on the other hand, we do get no semicolons. And we also have to choose where the brace goes anyway. This forces our hand. We consider that a win, and GopherCon can fix it anyway. The next token is actually inside the body of the function now, which is the fumped identifier, which of course came via the fumped import. It is not a coincidence that it's the same word, but of course it didn't have to be. It could have been a different name. And this brings up the point about readability that I think is important to the way Go works. And again, sort of flowed out of the design process. Every identifier in a Go program is either local to the package or it's a qualified identifier with a dot in the middle. And that is a profound effect on readability. You don't get this idea that when you do an import, the identifiers come into your namespace. What happens is one identifier comes into your namespace, which is the package name. And all of the package name component, all the package components are bound to the package name as kind of a little namespace, or if you like, sort of pseudo structure. That means that you never have to look very far to figure out what an identifier is inside a Go program, and that's a really important aid to readability. I also should probably point out that this word is fumped, not format. That's my fault. I will tell you right now, it never occurred to me to make it format because I knew that you were going to type this word, however it was spelled, in probably the majority of all Go programs ever written because it was the formatted print generator. And by the second or third time you typed it, you knew what it meant. It did not have to be the full format word. There are people who disagree with that. I respect their opinion, and I move on. Okay. The next token is a period. There's actually a lot of uses for the period token in Go. It means a lot of different things. It could be accessing an element of a package, an element of a structure, a method call, a function call. Early on, I remember Ken complaining that we had too many uses of dot, and he wanted syntactically to have a different character there to split the uses out for something. It might have been method call. We pushed back and convinced him it was okay, and he acquiesced. But it does mean that when you see just A.B in a Go program, you don't actually know what it means unless you look up A and understand the type. And you can parse Go without a type system, but you can't analyze it semantically without the type system. That's fine. But it does mean that you have to understand what the types are of an expression to know what it means. I don't consider that a problem, particularly because in practice, humans seem to have no trouble with this. When they see the dot, they know what kind of a dot it is. It doesn't bother them. One thing that does come up here, though, is that there's no, what would in C be called the arrow operator, the points to operator, because if the thing on the left side of the dot is, say, a structure pointer, and the right-hand side is a field tag, field name, you don't want to have to type *thing dot field. So we automatically insert indirection operators for you in order to avoid having that operator. That adds yet another meaning of dot, but one that we're quite happy with. I think the programs just look nicer as a result. Println. Notice it's capital P instead of lowercase p. That's because capitals are there for export. You all know that. I don't need to beat that up. I'd like to talk for a minute about the design of this thing, though, because it's actually a little bit of a story. We always knew that formatted printing was going to be reflection-driven. It wasn't going to be like in C where you have to explain the arguments, because that's not type safe. You have to actually understand the dynamic type of the object you're printing in order to safely be able to print it. Also, maybe even more important, because you know the type of the thing when you're printing it because of access through reflection, you also don't need a format. And so you can actually have a println in Go, which you can't have in a more weakly typed language. And so we knew that reflection would get us there, so println made it possible. And I think, in fact, most of the time people don't use format strings unless they're like formatting fancy error messages or something. Print or println does the work for you. And that's a consequence of knowing from the beginning, even before we understood how reflection was going to work, which was itself a very long story. We knew that that's how it was going to work, and so we designed for it. Println and his friends, they're all variadic functions. Go is very strong in variadic functions. The original form of a variadic function just had ... there, which actually came right out of C. There was no type on the ... It was always empty interface implicitly. And then one day Russ said, why don't we just make a type there? And so we didn't quite know what to do with that yet. Of course, it turned out to be a really great idea. It took us a while to get there. But on February 1st, 2010, the empty interface went onto the ... And so the signature of println became properly defined then. And the idea of the relationship between ... and slices became general and actually quite powerful and very easy to use. Open parent, not much to say. Traditional function syntax, no messages, no function application with space. It's just old school open parent. Then we have a string. Now, I picked a string here with some Unicode characters in it that says Nihongo, Japanese language. Pardon my pronunciation, Japanese gophers. One of the most important things about Go that was settled very early is that the input source is defined to be UTF-8. Now, since Ken designed UTF-8 and I helped roll it out with him, you knew there was going to be a UTF-8 language, going to be very strong. But I think it's really important to point out that we just declared up front Go is a UTF-8 language, period. There's no encoding question. You're not allowed to write it in some other language, because that means one thing happens beautifully smoothly, that if you don't define that, it doesn't work very well at all. And that is this string here, this thing with the Nihongo in it, you know the representation of those characters in the source code is UTF-8. And so it is well defined what non-ASCII characters look like in the source code. It just falls out automatically that the representation of strings outside the ASCII plane is UTF-8 characters in the source code. It's kind of a magic trick. There's nothing there, and yet it just works. And it's hard to explain in a way that makes it sound interesting, but it's true. And I think it's really important to understand that. And no other language that I know of actually does this. I'm sure there are some, but all the predecessors that I know of certainly did not define this way, and so they struggle with the meaning of a large character value. And then, of course, there's a whole question of what a string is, and it turns out it's an array of bytes with a couple of special properties. The string literals are the most important part of it. It was actually one of the very first things we wrote in the Go spec. It was written probably that first week, and it's hardly changed at all since then. Every detail of that was understood very well up front because, of course, we'd played in this space for quite a while. And if you want to know more about it, a few months ago I wrote a detailed blog post, which is probably a better place to read about it than have me blather on. Then you get to the closing paren of the function call. Of course, there's no semicolon there. The semicolons went away shortly after the release. I just made a wonderful change to the language. I loved it when it happened. But I should point out that before then, semicolons were optional in a very confusing, hard to understand, constantly changing way. We struggled with the grammar. I think at one point there were more productions in the Yak grammar to deal with optional semicolons than with the language proper. It was really difficult to sort that out. And one day we just said, I think Ken actually came in and said, why don't we just fix this? So we went back to Martin Richards' idea from BCPL, got rid of semicolons by injecting them in the lexer. And it changed the language a little bit because you had to format differently, but I think it was a huge win. And closing brace. And there we are. That's the end of Hello World. There's a whole bunch of things I didn't talk about in this program. I didn't talk about the types very much, what constants are, they're kind of magic in Go, methods, interfaces, how the libraries work, how memory management is. It was garbage collected from day one. We never considered any other option. Concurrency, of course, which is coming up. And then there's the various tools, the ecosystem, the community, the outside world, the ecosystem that develops around that. And I want to point out that although I've talked entirely about the language so far, the language is central to this story, but it's really only a small part of it. It's the entire thing that builds around the language that makes success happen. And the factors that bring that success in are, I think, building on the history, understanding through a lot of other languages and years of working in software development, what matters in a language, what doesn't matter in a language, the experience that comes from working for a long time, the process of design. Almost all of Go was defined in the first year and a half or so by Ken and Robert and myself, huddling down, arguing, debating, disagreeing a lot. Nothing went in until all three of us agreed that it was a good idea. And that's because we all came from very different backgrounds. And so it was important to understand that if the three of us agreed, it was probably a rock-solid idea. I think it's a really important part of the Go story. And later, of course, Russ and Ian and others came in and helped us make it much, much better. But I think this idea that you have a small team designing it and not just sort of taking a suggestion box and making things happen is a huge part of why Go works the way it does. But once we'd sort of got to where we thought it was right, we stopped. We said, this is it, this is the language. Go version 1 comes out and locked it all down. And that's a huge part of the story. I'll come back to that point. Now I want to go through a second program. That was Hello World. Now we need to talk about concurrency. And I think a good way to do that is to somewhat more quickly go through the first concurrent program that I ever saw, period. And that was first one written in Go. It came out of a paper written by Tony Hoare in 1978 called Communicating Sequential Processes. And the problem is, of course, the prime sieve. What we want to do is to print in ascending order all primes less than 10,000. It uses an array of processes called sieve. And each process generates a prime, passes it down to the next one, and there's a chain that develops of filter processes that filter out the details. I suddenly lost, oh, there you go. In 1978, this paper appeared. It actually showed this whole thing. Hoare credits David Greaves with this beautiful solution. I should mention in passing, this is not the Civ Veritasities. It's not very efficient, but it is kind of beautiful. Look at it. This is the original one. This is the complete presentation of the program in the CSP paper. There's no description of how it works. You have to puzzle it out. And I won't go through it all. I'll just point out two important points. Everything is in here. There's actually sort of a vague select statement down the left column. The star is a loop over all of the Civ processes. There's an array of processes, which is instead an interesting idea. And it's fundamentally the same program that you probably know, but it's just structured a little differently on the page. The other important point is that there are no channels in this. It's a rigid structure. There's just a fixed set of 100 Civ processes. 100 is known to be enough because it's the square root of 10,000. It's a theory paper. He's proving a point. That's fine. But because the original CSP had no channels, this is the best you could do. It's still an interesting program, but it's not very flexible. So about 10 years later, I had been futzing around with some of these ideas for a while and decided I wanted to play with them for real. And so I wrote a little toy language called Newsqueak. And Tom Cargill wrote the prime Civ in Newsqueak first. I think he credited Doug McElroy through it, but it's a longer story than that. This one, however, uses channels. Newsqueak had channels in it. And so the length of the run of primes is entirely programmable. The program is much more flexible. For modernized, it's a little easier to read, I think, even though it's a weird little language. I will point out that I don't actually know where the idea of channels came from. I don't claim I invented it. I really don't think I did. But I don't know where I got it from. It was floating around somewhere. And the later CSP book has channels in it, but the original paper does not. But anyway, NewSqueak had channels. You can probably read this program and pretty much understand what it does. It's probably, it's atom breading a lot of Go's properties. You can see a couple of key points here. The left pointing arrow operator for communication. And the next slide, you can see the colon equal guy squeaking in. And keen eyes will also notice a mook, which became make in Go, but that's just a coincidence, sort of. This program runs, by the way. Yeah, it's a very long line going off to the right. We should fix that, Andrew, wherever you are. But it prints them all. Jumping ahead, 2008, March 5th, we actually started writing the spec in Sydney on March 3rd, 2008. 2 days later, Robert said, let's write a program. And so into the spec, we typed this version of civ.go, which I think is correct, but it's very different from the language today. You can notice that those are pointers, an issue that we struggled with for a long time. They're pointers to a built-in structure that gets built. They still are. They just don't look like that anymore. The operators for send and receive came from the shell, greater than and less than. And you can recognize the program, but it's a little different. And it, of course, you'll notice, one other thing, you'll notice that main is uppercase. That was the early days. It might have been my fault. I think I was typing. But you can recognize, you can actually understand this program in modern Go terms and translate it pretty easily. But it mutated quickly. In July, we decided that greater than and less than didn't work because it was confusing to have unary operators when there were already binary ones with a completely different meaning. So we changed them to be these weird little funny sort of pseudo arrows. That helped a little bit. Channels were still the pointers, but at least we got rid of the capital on main. And so it's a little closer to current Go, but it's still kind of weird. And then about a month after that, there was a discussion where NewSqueak's operator came in. It got a lot nicer. We now had prefix arrow for receive, infix for send. Channels are still pointers, though, and so there's still some confusion about how you make a channel and what it does. But you can still see the change happening. Notice that, for instance, chan, it's a new chan int here rather than a make, because on early January 2009, we finally figured this out. We split new into new and make. The things that were pointers to built-in structures were called make, and so channels were made rather than newed. And that, some people still struggle with that concept. I don't think it's hard, but it is clunky, I admit, but it does the job. The code, however, is wrong in this example. This is out of the spec on that day because there's still a star left, and the channel types on the filter function are completely garbage. We didn't run it because, again, we were idiots. So this doesn't work. But then just before the release, I finally said, we should probably make sure the civ program actually runs in the spec. And so I went through, and sure enough, it was broken. So the capitalization now is gone. I brought in fumped. This guy actually runs. And this is modern Go except for the semicolons, which went away on December 10th, 2009 in the great semicolon purge. So this is the program that, you can recognize it all the way back to NewSqueak, really. But it mutated very slightly, but converged fairly quickly. The piece that's important here is that the historical refinement of through languages, through thinking about the ideas that are there, is again this process of history and decision process and time to get us to here. So this beautiful solution was contributed by a decades-long process of design. One thing I did not discuss that's extremely important to Go is select. A lot of people read about Go or knew about concurrency from other languages and will play in their language of choice and implement channels and coroutines and say, look, it's Go-like. It's not. If you don't have select, you don't have concurrency. You don't have real concurrency because it's a connector for channels. Without select, all you can build is linear structures. You can't build the interesting trees and loops and other complex structures, which are the key to building true systems that use concurrency well. And also, I'd like to point out that select is the only part that's really hard. Everything else is easy. Channels are just queues. What's the big deal? Select, though, that's tricky to get right. It's also tricky to design right. And Go's select, again, is the process of refinement through a series of predecessor languages originating with CSP to get the semantics right. And in Go, we spec'd it out on March 26, 2008. And at that point, we knew some of the things that needed to be fixed for the select in Go included making sure it could be implemented efficiently, making sure it's scaled right, getting rid of some of the features of select from other languages that were nice to use but made made things too complicated or too hard to make highly efficient. But that aside, the Civ program that I just showed you from 2009 is exactly the same as the one in the spec today. So that's almost 5 years with no changes whatsoever. And open source systems are usually not that stable, right? They get tweaked and work, certainly ones that are used. They're always being adapted, changing. And that's a good thing because you can make them better. But I think it's important to recognize that one of Go's key elements of success was stopping the change at some point. And we just said, Go's done well enough now. It's not perfect, still got a lot of problems. We know we screwed up a bunch of things. But it's better to just say we're done than to say we'll fix that and keep breaking people's programs. It's a really important reason for Go's success. So this is the trends graph from trends.go.com for the keyword Golang. Down the bottom, those two dates are 2011 and 2013. Go 1.0 came out in mid-2012. And I think you can see there's a distinct bend in the curve. It got suddenly much steeper when Go 1 came out. And I think that's evidence that people really need that stability in order to trust that they can use this system and make something out of it. It's a really important point. And so looking back, what are the factors for Go's success? I'm obviously biased. I was in the middle. I don't know why you guys like it. I know why I like it. But I can take a guess at what matters. The features and tools are obviously important. Everybody talks about how great GoFumt is and things like that. The concurrency is a huge draw. Having a nice statically typed language where nice and statically typed don't often go together is nice. The concurrency is a huge win. People love that. It's also, I think, one of the draws that brings people in for the first time. Having a strictly garbage collected language has its issues, there's no question about it, but it makes the language very attractive to start in. The compiler being fast, the binaries running quickly, this notion of static type and dynamic field that we tried to get right. Having a really good standard library, but limiting what it is so that it's outsiders can bring in more stuff. We don't have to put everything in the core. Works really well. The tools are critical to what happens, the Go command, Go fix, Go fumpt, things like that. But also the factors which were part of the design process all along to make sure those tools could be built, that the grammar is easy to parse, fast to compile, that the language doesn't have fancy semantics, that it's easy to read, easy to understand, easy to translate. Those are all important factors too. I mentioned GoFumt many times. This other concept, which I talked about in a splash talk a year or so ago, that Go was always designed for Google internally. And we're a big company with a lot of programmers. And we want to make sure that the language works for large teams working on large programs. That's sort of an intangible thing, but I think Go has a lot of features or lack thereof or design elements to make sure that programming large really works. So less obvious than those things I just listed is sort of the process by which Go came to be. We started with the idea that we needed a language to make it easier for us to get our jobs done. And our job is writing server software. And so we stayed focused on that idea. We're trying to solve the problem of writing server software. There's this process we went through of concentrated development, really intense for several years, followed by a freeze. We planned for the freeze, we worked hard to get there, but then we stopped. The language is done. And so that was a huge, this concentrated effort, understanding, really being involved, but then knowing when to stop is important. This idea that it was the consensus-driven design by a very small team is not unusual exactly, but it's not how everything gets built. And it really is important to the clarity of the vision of the language. But then, of course, it went open source. We got incredibly important contributions from a community that I'm happy to say seems to get what this is all about and appreciate what it's for. Go wouldn't be anywhere if it wasn't for you guys. And so the consequence of all this is we developed this really rich ecosystem of externally provided libraries and tools. The port to Windows was done entirely in the open source world. That's fantastic. That's a consequence of all of these other things tying together. So in other words, Go succeeds because there's an open source community that understands our mission and helps us achieve what we want to do, which is to build something good for today's world. So that brings me to my final point here, which is what I call fitness to purpose. In March, a month ago, this guy, Donnie Burkholz, maybe he's here, I don't know, wrote this article on RedMonk, entitled Go, the Emerging Language of Cloud Infrastructure. Now, the emerging part is cool. I love that. But if you drop that, it would say Go, the language of cloud infrastructure. That doesn't really surprise me because Go was designed to be a language for cloud infrastructure. That's why we did it. That was the whole point. We used to call those things servers. Now it's called cloud infrastructure. It'll be called something else next year. But that's what we did. And this is, I think he wrote a really nice article about why Go is succeeding and defining that it is succeeding. He's got this lovely little graph here. And again, it shows that sort of distinct kink in the curve and very steep lines to the right, which I think is very encouraging. And so that brings us to the next phase, which is the future. And that's where you guys come in. So we're passing the torch off to the open source community. Make something exciting happen. Thank you very much. Q&A? We have questions? Time for questions. Okay. Anyone have any questions? There's a microphone roaming.
Are there any plans for a debugger? I know
there are plans for a debugger, but they're very sketchy.
Yeah.
It's hard because the operating systems today don't want you to write a debugger. I'm serious. It's really hard. But yeah, we're playing around, but I can't promise anything. It might fail. But we're trying. We've got some ideas. Yes?
So I kind of have a pair of questions here. The first one is having Go be a target for, say, embedded use. So obviously there's some operating system issues around that. And then the second is supporting DSOs or DLL kind of shared object support.
They're closely related. We never expected Go to be an embedded language, and so it's got serious problems because it needs a fairly large heap to work well. Binaries aren't very small because of all the type information they need at runtime. It might work modern embedded machines are enormous, so it can be done. You can run Go, as an NDK on Android. But it's clear that we have to do something about DLLs in order to make this world work, and there's effort underway in the open source community. It's not clear where it's going, whether it's the right answer, what's going to happen, but for things like Android, I think something has to happen, and we're trying to make it happen. For the general question of embedded, it depends what you want, what exactly you need. In some situations, it might be a fine answer. It's never going to be real-time language, for instance. So, don't know yet. But it wasn't the design, so it's always going to be a bit of a weird fit. Wasn't the intent.
First of all, thank you for the awesome language. So after you deprecated NetChan, is there a first-class replacement for that? Have you come up with that yet?
I would love something like that. The original thinking around channels for about 2 days was trying to make them coupled to the network directly. We kind of gave up on that. And there was discussion about trying to have types flow through channels, and that didn't work out. So we kind of backed down. There are a lot of issues with doing channels over the network. They have, it's very difficult to get the synchronous semantics, for instance. You pretty much have to be asynchronous. That's a good thing and a bad thing. Erlang works really well, but they only have asynchronous message passing. There's a talk, I think, in this session maybe, anyway, sometime today, about someone who's tried to play around in that game. He's done some work in the runtime to support that. I have sketched out about 20 different ways of doing it, but haven't implemented any more of them. One day. I think you need a little more power from the language in order to make it work, and we don't have that power yet.
Hi. I was just interested really quick, going all the way back to the beginning of the talk, obviously you talked about what you guys were designing for, your consensus and all that. Can you just speak to even a little bit more or give one or two examples of you personally, obviously where you were trying to use those other tools and what you rammed your head into where you decided that you needed a new language? What were the problems you were facing? What didn't you like? And what were sort of those moments of inception where you had finally beaten your head against the wall to the point where you said, okay, this isn't going to work. This is failing here. This is failing here.
I've talked a lot about this before. Yeah, summarize it. We were writing in mostly C++ and some Java, and both of those languages just seemed to be too ponderous to work in. C++, you have to separate .h and .c. You end up writing the type specifications over and over again. In the environment I was working at the time, in the binary I was working in, builds were taking 45 minutes. I considered that painful. When builds take that long, you have a lot of time to think about what you might make better, right? Java isn't nearly that ponderous, but its ponderousness comes in a sort of culture of sort of long-windedness that's exhausting. And the understanding the error messages from compilers with a weird type system or confusing, it just seemed like we weren't productive, right? I'd gone from an environment working with a bunch of tools that we built in the Plan 9 world at Bell Labs, and went to Google, and we built some amazing stuff at Google, and we got it to work, but it was never, the actual process of building it seemed to be too heavyweight, and the language wasn't helping, the compiler wasn't helping, the tooling wasn't helping. It just seemed like I had to say the same things over and over again. So we tried to build we looked into a language that that compile faster and look nicer on the page and be closer to the way we used to work. And there's no question that relative to the modern big languages like C++, D, or Java, Go looks like a bit of a throwback, at least to the people who love those languages. But I'm okay with that. Yeah.
During the language design, what were your discussions or thoughts about a macro system, so that things like, if error not nil, return error, didn't have to be
I think the first mail said no macros, and that was the end of the conversation.
Fair enough.
I'm pretty sure that's true.
Looking to the future, are there any plans for more analysis and concurrency to be able to take common idioms like producer-consumer and special case that to bypass the scheduler?
There's two parts to that. One is the runtime needs to know, or the runtime in the language have to cooperate more to understand patterns better. And we talked a lot about doing some things along those lines. Not too much has happened, but I'm not claiming it never will. One thing I'd like to be able to see, it's the one argument that I think makes the current type system not quite good enough, is that it's very hard to write concurrency libraries. You can't write a statically typed mux or a statically typed fan-in or fan-out structure. And it'd be nice to be able to do that, but it's not sure the cost is worth it. So we talk about these things a lot, but there's no plans to do anything yet. You should have a microphone so you can hear it at home.
Corollary to that, you mentioned language and the runtime working together. Would the team really be willing to make language changes just for special casing?
You don't have to necessarily do it in language changes. I mean, it could be just that if you write this, it works this way, which is consistent with the current language but runs faster. Okay. We already do things like inlining and magic tricks in the runtime. The language semantics are not going to change. We can't do that. I mean, unless Go 2 happens. Yep.
Hi. What is the status on library versioning?
Go 1.3 beta is cut.
No, I mean dependency management and version.
That's something that the open source community is working on. We're not doing anything about it.
Okay, thanks.
What is your philosophy around making breaking changes in the future for Go?
It's written down. We won't. If we're going to break things other than for like security issues, which may come up, it's going to have to wait until there's a thing that's not called Go version 1. Might be called Go version 2 or something. Because that stability is really important. Breaking changes are called breaking changes for a reason. They break stuff. We don't want to break people. Seems like a sensible thing to do. Any more questions? Where's the microphone flowing? There's somebody in the front here. How many of you have your Gophers here? Can you hold them up for me? I want to see if I can get over 1,000 Gophers in a room.
Derek Collison, if you're here, would you go back to the corner, please?
Thank you. All right, maybe last question. Yep. Thank you.
Are there any plans for generics?
There are no plans for generics. I said we're going to leave the language. We're done. Yes. Okay. I think I should probably stop and let the next speaker come up. Thank you very much, everyone.
Yeah, we have Derek on the way. You had a last question? Hey, Rob, do you have time for one more question while we work on getting Derek up here? Do you have time for one more question while we get Derek up here?
Rob, what's the language history that led you to choose to do errors the way that we're handling them now?
The thing about errors is that they're not anything special. They're just values in the language like anything else. I know the mic here. Languages, the thing about errors is they're just they're errors, but they're just values. You have the entire programming language at your disposal when you want to program around an error. And since errors are a common feature of any program, you should have the entire language at your disposal. You shouldn't need some special mechanism like a try-catch or something. You should be able to just write an if statement or compare or print them or whatever. So errors are not special. That's the defining point of them. They're not special. All right, thank you.
Thank you, Rob.